Let me put the recording as well, 1 second. Okay, let's start. Starting with the first part. This trichloromethane, hopefully you can see the screen. Everyone can hear me properly, right? I said there's trichloromethane and there's propanone, and he's saying that both organic liquids, the molecules within each liquid are attracted to each other by relatively weak. So they've got permanent dipole interaction. So when trichloromethane is mixed with propanone, so there is the ketone group has a dipole, and so does because the Cls are more electronegative, so the H in trichloromethane is going to be positive because all the electrons will be closer to, they're going to be more attracted to Cl. So you got a dipole attraction. So yep, they've got a dipole attraction. So a student plans to perform an experiment to investigate the strength of the electrostatic attraction by finding the temperature change when equal volumes of trichloromethane and propanone. So he's saying what will happen to the temperature change when propanone and trichloromethane are mixed together. So what's going to happen? What will happen? Temperature change, will it increase or decrease, and why?
Decrease.
Why?
Endothermic reaction.
No, but they didn't say it's endothermic. So what is happening basically? Okay, there's a bond being formed, right? There's an attractive force that is being formed. What is bond formation? I mean, not just bond formation, any attractive force when it forms, it is exothermic.
Exothermic.
Yeah. So initially, I mean, previously they were not attracted to each other because they were not together. But once you mix them together, there's going to be a permanent dipole attraction that's going to be formed. And if there's an attractive force that's being formed, that is exothermic. Bond formation, remember, is always exothermic. If you want to break the bond, then that's endothermic. Okay? Is this idea clear?
Yes.
Okay, so there's bond formation happening, and that's obviously exothermic. Now the student is only given the following equipment and chemicals for the experiment. So 25 cm2 thermometers, measuring cylinders.
Sir, the temperature decrease ही होगा ना?
Increase होगा ना?
Oh.
Exothermic where temperature energy is released, right? Whenever bonds are formed. I mean, this bond is getting formed, right? So heat energy is produced, that increases temperature. Temperature hamisha, you always measure the temperature of the surrounding. So when a substance releases energy, the temperature always increases of the surrounding.
Sir, I can't hear you.
Can you hear me now?
Yes, sir, you are audible.
Okay. And so now next one is the student is given the following equipment, and beakers and measuring cylinders and thermometer. Outline the method student should use in this one experiment to find the temperature change when trichloromethane is mixed with propanone. Give details of the volume of liquid used and any readings that are taken. So I guess volumes used. You've got a 25 cm3 beaker, right? Now, so basically the only thing you have to be worried about is that your two volumes of trichloromethane and propanone, they don't exceed 25 cm3. So I've got a measuring cylinder. So what I'm going to do is I'm going to take 10 cm3 of propanone. I'm not going to fill it up till, I mean, I could use 12.5 as well. So 10 cm3 is fine, I guess. So 10 cm3 of propanone and trichloromethane. So that should not exceed 25. Now, readings taken. There's only one reading that needs to be taken, and that's the temperature change. You're going to place the thermometer in the beaker, and you're going to measure the initial temperature. And he's adding, I think, what is he adding? He's adding, I mean, there's propanone, so there's going to be initial temperature of the propanone, I guess. And what we can do is we can separately measure them in the measuring cylinder. There are two measuring cylinders, right? So there's a measuring cylinder, and there's another measuring cylinder. So what you can do is you can measure the initial temperatures of both and the final temperature of the mixture. Now that final temperature is going to be your maximum temperature. Remember that. I mean, there's no reading called the final temperature. It's just going to be the maximum temperature that is reached. And then he says method used. So what is the method that's used? Do we have? I don't think we can time it, because I don't think they've given us a stopwatch. So give details of the volume used, and so I guess that's it. The method used is going to be the maximum temperature reached. So I guess that's
Sir,
yeah.
why are they using 10 centimeter cube of propanone?
You see, the beaker that you're mixing it in has a maximum capacity of 25. So this,
Mhm.
so you're going to take 10 cm cube of propanone and 10 cm cube of the other one, trichloromethane. I mean, it should not exceed 25. You could have taken 12.5 and 12.5. Is that clear?
Yes, sir. Okay.
So I think in the method used, you're just going to write that. I'm going to write this in detail. That measure temperature change, initial temperature of the two liquids in the measuring cylinders. Then you're going to mix the two liquids in the beaker. I mean, you're not going to call it liquids. You're going to name them. So you mix the two liquids in the beaker, and then you just try to find out the maximum temperature that's reached. That's it, 3 marks. Is that clear?
Sir,
Haji.
sir, is it better that we always take lower the amount of the limit they've given to prevent spillage?
But that's what they're looking for. But you remember 12.5 is also fine, because 25, if it's a 25 cm cube beaker, that doesn't mean it's 25 till the top. I mean, the reading or the graduation usually stops at a certain point below the top. So even then, it's not going to be spillage, but it's better still to keep it not completely full. Is that clear?
Yes.
कुछ भी हो सकता है ना, you have to take into account, maybe there could be spillage. Maybe you're trying to stir it with the thermometer. You could write that stir the solution so that they mix well with the thermometer. The method can, then you can add that. I mean, you can check the marking scheme. Probably they would have written a very simple explanation. But okay, let me just, because it's which one was it? I missed just a second. Is this the one? Just okay, so 2 equal volumes, that should be less than 25. So this will be at that. Measure the initial temperature of the liquids, leave to equilibrate. Equilibrate basically means that you leave till the temperature becomes constant. Right? I mean, right at the start. So I think that is missing, because when you try to measure the initial temperature, I mean, the method should have included that. Wait for a while until you've got a stable initial temperature, or until it stops changing. Equilibrate means that it reaches an equilibrium, because maybe your liquids are slightly higher than room temperature, slightly lower than room temperature, so their initial temperature would be changing. So you have to ensure initially. Remember, in any experiment, I mean, this is important, that this initial temperature, I mean, this is an important point. That point is missing. That you have to ensure that your starting temperature, or the initial temperature, is constant and it's not changing, it's not varying. Okay, so you have to measure it for a certain while, like 1 minute, and see whether there's any change happening. If not, then you're fine. Then that's your initial temperature. And what else did he write? He wrote, where's the mix the two liquids, monitor the temperature, or starts, or the maximum temperature. We read the maximum temperature. So I did not go for the stopwatch, because I don't think we have a stopwatch. We just read the maximum temperature that was reached. So next one. The apparatus used leads to significant heat loss. So state one improvement the student could make to reduce heat loss. So how could you reduce heat loss in this experiment? Or in any experiment, how do you reduce heat loss?
Cover the beaker with the lid.
Or
So,
insulate it? Can that also, like, the insulate the beaker? Would that work?
yes, it will work. Instead of the glass beaker, that will work. Or the glass beaker itself is a very horrible piece of apparatus. You use a styrofoam cup. So you always use a styrofoam cup.
To let it cool down in a beaker.
Insulate the beaker is fine. There's nothing wrong with it, but it's much better to actually use a styrofoam cup. You always do heating experiments in styrofoam cups. Now, part C, trichloromethane and propane are both volatile and flammable. State one relevant precaution that should be taken when carrying out the experiment. So they're volatile and they're flammable. I mean, so what do you need to do? Just keep anything that keep flames away. That's it. Yeah, that's it. So, and volatile means that it will vaporize. So it would be very easy for it to catch fire because it will turn into a gas. Now, state one change apart from reducing heat loss that could be made to improve. Now, remember about accuracy. How do you always improve accuracy? Timing
Repeat the experiment?
No, it's by repeating the experiment, you cannot improve the accuracy. I mean, there are two things: repeating the experiment, taking average. That just proves that the results are reliable. There's a thing called reliable results. Reliable results are repeatable results. It removes anomalous values. Like maybe you did one experiment wrong and the values were slightly off because you did some terrible mistakes. You did 2-3 more experiments and that mistake was not repeated. So you were able to figure out which of your results were actually repeatable or reliable. So by repeating experiments, you get reliable results. Remember, accuracy can only be improved by the system. If you improve the system's accuracy, like heat loss is a systematic error. Like if you have heat loss, no matter how many times you repeat the experiment, there's always going to be heat loss. You get the idea that there's a different, reliable means different thing. Reliable means that how repeatable are your experiments? Accuracy depends on the system. How could you improve the accuracy of the system? So getting rid of heat loss, that's one. And I mean, they did ask for that, but they said apart from that, the other method of improving the accuracy is by having a more accurate apparatus. So how can you make the apparatus more accurate?
We can use a burette.
You can, yeah, you can use a burette. I mean, that's fine. A burette is fine. A burette is a lot more accurate.
सर ये volatile वाला जो था इसमें हम लोग लिख सकते हैं कि since gases are formed we can use safety glasses or goggles as they say.
No, lekin he didn't say that there were poisonous gases. He didn't mention that, right? Like he didn't say they were. I mean, he said they were volatile. I mean, it was volatile and it would turn into a gas, but he did not say that the gases were harmful. So
There is a term called flammable, so we can use the gloves.
it was flammable. So the only thing is you just keep it away from flames. That's it. I mean, the only trouble with the volatile part was that they were flammable. If they were poisonous or they caused irritation or something, then you would use goggles. Then that would be the appropriate answer. But I don't think not in this case. Like the gases are harmless, right? So why use goggles? There's no point in using goggles. The more important thing was that the gases were flammable. So that's why you're going to use you're going to just keep them away from flames. That's it. Achha, is this part clear about accuracy? And let me open the notes as well for paper 5 just a second. This one. Tika, I think I've shared the board with you once. So about just wanted to mention in a bit more detail. Where's the?
Sir, could you please send this on the group chat?
I'll share the board link. I mean, this is 1 second.
Okay.
I'm adding it 1 second. Basically, I just add all the points over here. So I wanted to where's the accuracy part? Just a second. Yep, this part. So what I wanted to there was somewhere where I had in the board mentioned accuracy. I wanted to explain a few things. And it must be here somewhere, TK. I've written it before, but just can't find it. Accuracy. Yep, I think this one. So over here, so remember, reliable are close to the line. Reliable means anomalous points. Reliable means repeatable experiments, right? It just means repeatable. It does not necessarily mean accurate. So you could have really poor results, and those results could be very reliable. And I'm going to talk. I'm just going to add accuracy over here. I think it's definitely mentioned somewhere, but can't really find it. So remember about accuracy. Accuracy is all about apparatus or the system. You make the system more accurate. More. So when they talk about improving the accuracy, so you can use better equipment with more precision. So you can use better equipment, or what you can also do is or minimize heat loss, etc. I mean, that's better equipment. Like if you use a styrofoam cup, you'll obviously decrease the heat loss. So remember, accuracy is very system specific. You've got to improve the apparatus. Now, one more thing about accuracy is that you can make the results more accurate by using larger values. If you use larger values, you're always going to have a smaller percentage error. Dealing with small quantities, your results are always going to be more inaccurate. Because, for example, if I have 2 grams and the device has an error of plus minus, let's say 0.1. So my value has a percentage error of what? Can somebody calculate this? What is the percentage error if I try to measure 2 grams and there's 0.1, there's plus minus 0.1 error in the device. So that means 0.1 divided by 2, so into 100. So what is that? 5%, right? But if I use the exact same device and this time I measure 200 grams, it's the same device. So the error is the same. It's plus minus 0.1, right? So what is the percentage error now?
.05.
Yeah, you sure 0.05? 0.05 or 0.5? So I'm gonna go with 0.05. Yeah, I think that's fine. So is this idea clear as well, that larger percentage error larger values using larger quantities, that would lead to more accurate results? Is this idea clear?
Yes, sir.
Yes.
And also remember, for example, if you want to make a very dilute solution in chemistry, you never actually make a dilute solution. You make an extremely concentrated solution. I mean, you've often noticed moles questions, right? Like when you're doing AS moles questions, you would have all often noticed that they would make a solution and then they would dilute it, right? Why were they doing that? Because making a dilute solution is very inaccurate, because you have to use a very small quantity, and it's measuring a small quantity accurately has a lot of error in it. So what they do is they add more of it, they make a more concentrated solution, and then they dilute it with water, and that's how you get a dilute solution. You never actually make a dilute solution directly. You always make a concentrated solution so that more mass needs to be added, and then you dilute it, because it's going to be more accurate that way. Is this idea clear?
Yes, sir.
So coming back to accuracy, Burette is fine. I mean, you could have improved the thermometer accuracy as well, because there was a thermometer as well. So you could have had a more accurate thermometer with more graduations.
for this question, like while rinsing the apparatus with the same liquid?
No, not. Yeah, that's also system specific. It's that will kind of lead to accuracy, but that's not. I don't think that's a very, because I don't think he. I mean, that is fine. There's nothing wrong with that. The only problem is maybe he's already rinsing it with the same liquid, right? So maybe that was never an error. So he didn't, since he didn't mention that detail anywhere. So how do we know that he's not doing that, right? But so I guess we can't really comment on that. Although that point is accurate. I mean, that point is good. But since he didn't mention like in detail, like how was he actually washing the apparatus or what, so we can't really comment on that. Dipesh, is this clear, this part?
Yes, sir.
So then you have and you could have used larger volumes. You could have taken a 250 cm cube beaker and you could have added 120 cm cube of both or 100 cm cube of both, and you would have gotten larger readings, and those larger readings would have a lower percentage error. I say anyway, so there's now I think that this is the moles question. So there's trichloromethane and propanone, and the energy release is 1.67. Calculate the number of moles of each compound in the mixture. So you're given the MR. So can somebody do this? It's 37.5 divided by the MR of 119.5. And this one is 19.75 divided by 58. So how many moles do we get for both?
Trichloromethane is a 0.314.
Okay, so you've got 0.314 and just a second, I'm stuck. What's the other one?
0.341.
So I think approximately kind of the same moles. As a calculate the enthalpy change of the electrostatic attraction formed between trichloromethane and propanone, you must include a sign in your answer. So basically, I think you always use the limiting reactant. So 0.314 moles produces how much energy? It produces 1.67 kilojoules of energy, and it's exothermic, right? It's negative, released, right? He says that it released. So 1 mole. Enthalpy change is always for 1 mole. So 1 mole would produce how much? That's going to be X. So what is the value of X? And also remember, always limiting reagent moles are used, because the other ones are not going to completely react. It's 1:1, right? I mean, initially they did tell us that one molecule reacts with one molecule, right?
Is it going to be negative 5.32?
So you're getting negative 5.32
E2.
kilojoules per mole. Yep. Now suggest an experiment the student could carry out to test whether the number of moles of trichloromethane affects the temperature change. So I guess the number of moles of trichloromethane affects the temperature change. So use a different one. Use different amount of trichloromethane, I guess. That's it. So repeat the experiment and use different volume of of trichloromethane. And so you're going to vary the volume and record temperature changes. That's it. I mean, so that would kind of give you an idea. If there's no change, then obviously no effect. So now the next question. The next question is lead nitrate. We'll try to and do this one quickly. Lead nitrate, it decomposes, produces NO2 and O2. The nitrogen oxides can be separated from the oxygen by cooling. The gas mixture produced. NO2 condenses and oxygen does not. Okay, fine. So this condenses. Draw a label diagram of the laboratory apparatus that could be used to prepare liquid nitrogen dioxide from the thermal decomposition. So when does it really condense? At what temperature? It's got a boiling point of 294 kelvins. 294 kelvins in centigrade, that's how much? That's 21 degrees centigrade. So that means you have 294 kelvins. That's I mean, can somebody just confirm that's 21 degrees centigrade, right? Minus
Yes.
270. Okay.
Yes.
So all you have to do is you just have to sort of lower the temperature below 21. So you can have a boiling tube. You can do the decomposition in the boiling tube. And remember, not a test tube. It's always a boiling tube. A boiling tube is just a better version of a test tube. You're going to put the mass of lead nitrate over here. And then what you're going to do is you're going to try and heat it strongly. So you're going to heat it. And you're probably going to have a Bunsen burner over here. This should be sealed tight. And there should be a tube that must be, this is where the gases are coming in. You can make sure there are no gaps. If they see any gaps, that means the apparatus, I mean, the gases will escape. So make sure when you're sketching, even if it's a bad drawing, make sure there are no gaps in between. There's a device called the U-tube, which is used as for condensing. You must have seen it many, many times. That's, I mean, that kind of looks like this. I mean, I can't really draw it properly, but so I'm just making a rough sketch now. So it's kind of like this. And that's again no gaps, TK. And this thing has to be placed in a beaker, which should have ice in it. So there's going to be a lot of ice that's so it's got ice in it, and that's your U-tube. Now remember, you can't use a condenser, because if you use a condenser, its temperature never goes to 0. It doesn't have ice in it. You need a very low temperature, so that's why you're going to use a U-tube. Is this clear, this part?
सर ये इसका boiling point 21 degrees पे है. इसका मतलब ये है कि room temperature पे ये experiment नहीं हो सकता.
No, it's not going to condense at room temperature, right? It has to be, you have to condense it, right? So it has to be lower than 21. So maybe make it like, when is it going to be a liquid? It's going to be at a liquid at 10 degrees centigrade or 5 degrees centigrade. Okay? So you have to like really lower the temperature. So your normal Liebig condenser, you can't use that. Is this clear?
So what does that U-tube do?
I mean, it's just something that will pass the gas through the ice and cool it. So the NO2 condenses over here.
So what is the meaning of that anhydrous?
The anhydrous means without water, I think. Where's anhydrous? I mean, it just means there's no water. So, Baki, there was a question. I mean, the ice, obviously you have to condense it, right? So when does NO2 condense? NO2 condenses at a temperature that's at less than 21. So the purpose of ice is to lower the temperature close to 0 degrees centigrade, let's say. So all the NO2 over here is going to eventually start condensing. Is that clear?
Yes, sir.
Yeah.
So if NO2 condensed at, let's say, 90 degrees centigrade, then you don't need ice. You could have done that with a normal condenser, like in distillation. You could have used the distillation apparatus, and you could have condensed it using using a Liebig condenser. But a Liebig condenser has cold water in it. Cold water at best will have a temperature of around 25. I mean, it's not even cold water; it's just normal tap water. So that could just lower the temperature to 25 or 30 degrees centigrade. It won't lower the temperature further. So for that, you need ice. So which is why we need ice in this case.
If we used ice, would it be wrong?
If you use which one?
If we used ice for the NO2, if it like condenses at 90 degrees, if we use ice, would that be wrong? Instead of using the cold water?
Even in that case, I think it will be fine.
Okay.
It depends, like if, but for example, let's just assume if that's the only information that's given, then I think that would be fine as well. Now this one, next one, you just have to write the units of Kp. So Kp is what they even gave you the expression. So it's and what pressure were they using? Are they using pascals or are they using? So they didn't mention what the unit. So we will just talk about pascals. So it's pascals over Pascal squared. So the answer is pascals to the power -1. Now he says a student plans to investigate the variation of Kp with temperature, and a sample of the mixture of nitrogen oxides is introduced into a gas range at 295 kelvins. The gas range is sealed so that it is both airtight and watertight. The volume occupied by the mixture is measured at different temperatures. The Kp value is calculated at each temperature. So name the apparatus you would use to heat the gas range at different temperatures between 295. So basically, he's got a syringe. Let's assume that that's your syringe, and it's got this, and it's got the gases, and you have to sort of heat it. So the temperature that you want to heat it is 295 to 370 kelvins. Like in centigrade, what is that temperature? 295. That's what is 295? That's 22 degrees centigrade, right? What is 370? 370 is 97.
Yes.
And he's saying you have to different temperatures between these temperature ranges. So how would you heat it? Like between 0 and 100 degrees centigrade, you have to vary the temperature between 0 and 100. What's the best way of heating it?
Heating rod.
That will lead to an extremely high temperature. So let me just show you the heating apparatus. So there's one second, where's the heating part? So this is the YouTube part. If you want to decrease the temperature, just heating. Now, one way is, Bunsen burner. That's the first thing. The problem with the Bunsen burner is that it has a very high temperature, around 800 to 1000 degrees centigrade. So you're never going to use a Bunsen burner. Bunsen burner is not suitable for this. So gentle heating. One is that electric heaters with a thermostat. That is one way. But how could you? I don't think that's a suitable apparatus in this case, because how would you heat a gas syringe? I mean, if it was a liquid, you could put it on a beaker and put it on this thing, and it will heat it till an appropriate temperature. But I don't think gas syringe would work with this. So I guess the better way is a water bath. You could place the gas syringe inside the water bath. The water temperature could be varied from 0 to 100. And the good thing about water is that its temperature does not change very quickly. Like if the water has a temperature of 80, then water loses energy very slowly. So it's got a very high specific heat capacity. So it doesn't lose temperature that quickly. So you could maintain that temperature with a water bath. That's I think for gentle heating, it's always going to be a water bath. Is that clear?
So
Yes.
when do we use these electric heaters with thermostat?
Like what I could do is I could use the electric heater with a thermostat with the water bath. Like if I want to heat a beaker, right, which has a liquid in it, I'll probably use an electric heater. Like if I want to heat a beaker to 50 degrees centigrade. So my only issue with that is that how would you heat a gas syringe with an electric heater? The apparatus would probably not work with that. I mean, electric heater is like a stove, right? Like you've got electric stoves. If you don't have gas stoves, you've got electric stoves. So it's like a metal plate or a plate it's like a hot plate. So it will work with something where you have a solution and you're trying to heat that. Is that clear?
Yes.
Yes, sir.
So water bath is going to be thermostatically controlled. So, and always write this water bath. That's thermostatically controlled. Now the next thing is you just have to fill the table. So 1 over T and log of Kp. Can you tell me what the values of 1 over T are? What's 1 over 377? And you have to write it to 3 significant figures. Okay, for this one, I'll just quickly go over this. I don't think there's much to it. All you have to do is you just have to plot these values, 1 over 377 and 1 over 361, right? 3 significant figures. So you're going to get these values. You've got log of Kp. So log of Kp, and remember log, when it says log, it's base 10 log. You can remember that. So you just take these log values. He's given you everything. So he's given you a grid and you have to plot log of Kp versus 1 over T. So basically these two things have to be plotted against each other. The graph is even labeled, so you can just make points. And a graph is going to be made. Where's the marking scheme? Maybe they've actually plotted this. Just a second. We did have the marking scheme somewhere. Yeah, actually they didn't plot the graph, but they gave us the values. So you're just going to mark the values, make sure you follow the instructions properly. If there's a point, always remember to put a cross. Always mark points with a cross. And I'm just making a rough graph. Maybe this is not the graph. You can try making the graph. So you'll get a bunch of data at different values. And then what you have to do is draw a line of best fit. Now, when it says a line of best fit, that does not necessarily mean a straight line. Maybe the data is kind of curved. So remember, a line does not mean straight line. It could mean a straight line, but you would have to check with the data. Maybe it's something like this. So in this case, you would have to make a freehand curve, right? So just make sure that line does not mean straight line. It could mean straight line. It depends on the data that you have. We can just check the marking scheme for this one that, so there's a line of best fit drawn. So, I mean, you would have to plot the whole data and then you have to see what happens. Now on the graph, stay and explain what your graph shows about the accuracy of the experimental results. So about the accuracy. Now he's talking about how would you know from the graph whether your results are accurate or not accurate from the graph?
If there isn't
the
any
values-
analysis,
I mean, like,
Sorry.
let's say this one. Let's say this one. Is this an accurate experiment or an inaccurate experiment?
An
Accurate.
accurate one?
Okay, that's an accurate one. If my graph had points like this, there were points going up and down, and that was kind of a very sloppy experiment. That wasn't a very accurate experiment. So what your graph shows about the accuracy of the experiment results, so it will depend. It's subjective. If you think the points are very close to the line, that means it's a good accurate experiment. And suggest a reason for your, so if there's less scatter or if there's more scatter, then suggest what the student could do to improve the accuracy of the experiment. So what did I tell you about improving the accuracy?
Taking large values.
larger values than the apparatus used.
Okay. So you're going to stay explain your graph shows the results are accurate and says reason. So what could you do to improve the accuracy? You could have one way to improve the accuracy of your graph is have more points. Like if you take more readings, like if there's a lot of, so that's one way. So have more values, more and improve you could improve the apparatus as well. But over here, I think it was very graph specific. Just let me say and explain what your graph shows about the accuracy of the experiment. Suggest reason for your answer. Suggest what the student could do to improve the accuracy of the experiment. So take more points. That is one way your graph will improve. And use the graph to determine the gradient of the line of best fit. So again, so if he's talking about the gradient, then that means my assumption that it was a curve was wrong. It was probably a straight line. So you can kind of make a gradient. I guess you know how to make a gradient. And give your answer to 3 significant figures. Finally, so we're almost out of time. Use the gradient. I'm going to do this one. Use the gradient. Now remember, you had a graph of log of Kp versus, that was your y-axis, and 1/t was your x-axis. So he's saying that log of Kp, and according to what I figured out from the question was that it was a straight line. So log of Kp is equal to minus delta H divided by 2.303 times R over T. So there's 1/t. I'm just writing it separately, plus a constant. Now remember, make sure you know how to compare equations with y is equal to mx plus c. Whenever you have a straight line graph, any equation could be converted, even if it's a quadratic equation, a log equation, it could be converted into a straight line equation by just comparing it. What he did was he plotted log of Kp, which was y, versus x, which he took as 1/t. So what does that leave? I mean, what does that make m? This thing is your gradient. You just calculated gradient, right? So what you're going to do is you're going to try and solve this. You did calculate the gradient of the graph. So it's going to be minus delta h over 2303 times r. And the value of r is also given. So the gradient m is known, the value of r is also given in the question. So you can find delta h and that will give you this answer. Is this clear? That, I mean, you're very used to this in physics as well. Any equation could be just by comparison with y is equal to mx plus c. You can convert that equation into a straight line equation, which he actually did. And m is your gradient. Is this part clear?
Yes.
And then you have, with reference to the data, so that's the last part, with reference to the data for Kp in the table, suggests how the color of the equilibrium mixture at 370 will differ if at all the color at room temperature. Explain your answer. So he's saying, how will the color change at 370, almost 100 degrees centigrade? How will the color change? So what was the equation that we were dealing with? It was this one, right? So the question is, how will the color change? Now it depends. You did figure out delta H. That was the last thing that you did. So I let me just check the mark scheme. The delta H was, it had a negative value. So if you increase the temperature, the endothermic reaction is going to be favored. So the equilibrium is going to shift backwards, and that would make the syringe more brown in color. That's your answer. So from the graph, we were able to figure out what delta H was. And when you increase temperature, the endothermic reaction gets favored, which would make it more brown. Is this clear?
Yes, sir.
So what's the answer for I, the one above it?
Which part?
The one after we calculated delta H.
Part, I mean, this one?
Yes.
Sorry, with reference to obtained state, explain how Kp varies with temperature. So I think that's given in the question. Like, where's the data? This one. Kp and temperature, right? Kp increases, right? When temperature decreases. Is that clear?
Okay. Okay.
So inverse relationship, okay, that's right. So that's that part. Okay, let's continue next time then. We'll have a class tomorrow as well then. Okay. Same time.
Thank you, sir.
Okay, sir.
Okay, everyone, take care.
Thank you.
Allah Hafiz.
Hafiz.